So I'm going to ask, unfortunately, I'm in a mode where I can't see anyone, but I'm going to ask the other presenters to initially turn on your video. My name is Scott Klasky. I'm a scientist at Oak Ridge National Laboratory. I lead the ADIOS project. The second presenter is Norbert Podorski. Norbert, can you just say hi?
Hi, I'm the second presenter. Been working with Scott for many years.
Thank you, Norbert. And finally, we have Anna. Anna, are you on?
I think she is MIA right now. She will.
Oh, Anna is getting a shot, we'll say. So with that, I'll start and try to help guide you through this presentation. As I said, ADIOS has a long history and many contributors. If you have any questions along the way, feel free to ask. You can type it in chat. You can ask by just turning on your voice and asking. We'd like to help. Normally, we do these things fully hands-on, but for this presentation, we thought this would be more of a lecture style where we'll show you everything along the way. So let's progress and go into software. So we're using a version for ADIOS. ADIOS has 2 releases per year, and ADIOS is very tightly coupled to ECP data reduction / compression technologies, including SZ, ZFP, and MGuard, as well as we have very good ties into many of the visualization frameworks. And here we're going to show things with Visit, and it's closely related to ParaView, along with work with VTKM and very tight integration to Python and Matplotlib. And as we said earlier, I'll just repeat, you'll always see the link to where you can download the PDF. There's a bunch of slides which are hidden in this presentation, but for just being complete, we have them included in the PDF. There's a video in this, which is why it's a bit long, but let me just continue and say there's documentation, of course, examples. You could download the source code from our GitHub repository, and everything was really redone. With ECP, we saw everything we did all these years and said, let's take the algorithms, let's take the ideas, and then let's just throw away the code. So we did that, and we have something which is just so much more stable at this stage. So there was a big change in the way that we work and all of the software engineering, which I think all of you have heard all the wonderful stories in ECP. So you can see where all these things are for help. Movies that you can download as well. Again, I'm just going to show this quickly to get into, so what are we looking at? And what we'd say is there's this big data problem. I think you've all heard it. And we were very flattered when John Luke and Axel, when they talked about ADIOS being a very critical part of their project. And that's one of the things that we'd like to tell you, that we really enjoy working with applications. We are trying to be very good with applications. So when we have different requests, we try to then make sure that we honor those requests, and we try to make sure that we minimize the I/O. So without saying too much, one of the big things that we'll say is we believe I/O is the data that moves from one point A, from a producer to a consumer, point B. And it can be multiple producers and multiple consumers. Each consumer and producer can run on tens, hundreds, even one process or millions of processes. And we try to test all of these different scalings as well. But when we move data, there's a huge amount of effort to make the data self-describing. So if you're familiar with different common self-describing data formats like HDF5 or NetCDF or things in XML, what you'll know is that you need to describe your data so that anyone coming in can read this. You don't have to just rely on the code that wrote it to be able to read it. So along the way, what we see is that in the evolution of computing, and this is sort of the evolution of ADIOS, where we began in 2001, and that's actually, before I got to Oak Ridge, I was sitting at the Princeton Plasma Physics Lab, and we went from machines that were running on 1,000 nodes or 1,000 processors. I'm trying to remember the Seaborg IBM SP2 system, up until now where we're at Summit, and soon, as you know, we're going to Frontier. And during this time, the figure on the right, which was made by one of my good colleagues, Ian Foster, and myself, we were kind of tracking how the file system fared compared to the amount of flops. And what you can see is that the prediction to 24 at the time when we wrote this paper was that we were getting roughly a factor of 100 times worse. Now, it's not going to be quite as bad. It's probably going to be a factor of 50, but that still says that we need to do I/O well. And what we've done through ADIOS from the initial release that came in 2009 to now is we kept on adding both more functionality along with a lot of software techniques, new algorithms. And this was always driven by how the applications were running and what the applications were doing. So going further into this, so what is ADIOS? And it's not just one implementation. There's a bunch, if you see on the slide, this figure, there's an API, which we'll show you many times so that we hope you fully understand the simplicity of the ADIOS API. And then there's these different circles, what we call engines. So ADIOS is an abstraction to allow for very high performance I/O. And I see many of my application friends on here from Fusion, at least. And what we'll say is we can use ADIOS to couple codes. We can do this for a strongly coupled code for two applications running together in the same HPC system. We can do it whether we have an experimental facility and use the same abstraction to move this even to an HPC system. And we'll have a slide on that. So what we're doing is we're providing the glue to workflow systems so that it can use this self-describing data. And then these different engines are highly optimal engines. And they're highly optimal for things such as checkpoint restart, strong coupling, loose coupling, wide area network data streaming, and even in-memory object storage. So all these different engines, and we add to the list, I noticed there's one that we'll talk about, the Inline Engine that came from Kitware. And these engines have a purpose. So then so one of the things that you do then when you're running is you can choose the engine. So you can change the engine so that you can make the ADIOS API work as if it's writing ADIOS, self-describing data, optimized for DAOs, for their object store, or going through GPU Direct, which is what you'll see on systems that have NVIDIA and direct attached storage to NVIDIA, or when we get over to Frontier. You can use ADIOS to write to HDF5, and similar in part of our project, we even provided a vol layer of HDF5. So using HDF5, you can write ADIOS. And the caveat in those statements is you get most of the functionality, but not all of the functionality when you go in between these types of techniques. These different techniques over here that I'm pointing to, from SST to SSC, these are for what we call staging or in situ processing. And it's fairly easy if the writer of these different technologies conform to ADIOS so that they could fit in so that then ADIOS can use these technologies. And as we say, we'll show many examples of where you can achieve over a terabyte per second. But, I pause for a second that it's not all performance. And when we work with projects such as the SKA project, where, I'll have a video about that. But with SKA, I mean, it's going to be the biggest radio astronomy telescope, and you have to make sure that the data that comes out is trusted. So you have to trust the code, and you have to trust that the data is going to be written. So there's an extensive amount of testing, and we say that we have almost 2,000 tests that go on every time there's a commit. So this has been something which has saved us a lot from the past, where there's always something that happens and we never know, is it the file system? Like, is it Lustre or GPFS, or is it the hardware, or is it ADIOS? And of course, whenever you're integrating directly to an application, the answer was always, it's ADIOS's fault. And of course, when we say, well, that was a MPI problem, it had nothing to do with ADIOS, we have to then be able to show and provide that support, because it's very confusing when you're actually integrating with applications. So let me just say again that ADIOS I/O calls, they are declarative in nature. So basically, it's which processes write what. And when you have a process, you have essentially a local array, and it can fit into a global space. So that, you have to think about where this fits. Is that just each MPI rank, for example, that writes separately? And then you can just say, I have n ranks, and this is just the 5th one or 6th one, and that's how it fits globally. Or is it that you have something spatial, and these are the areas that it fits? So, for example, in the WarpX presentation, when they use knapsack, they have blocks all over the place, and you need to know the locations. So when we talk about ADIOS and the strategy, that's like when we choose the engine, then things are very separate from the users. So then users don't have to really care about how data is aggregated for I/O, how many what we call subfiles. You may want to write one file, but that file may be many files. And the reason why is that's what's going to get the performance for you. So what we try to do is we try to eliminate most of the file system hacks that people do. And when you look at the data, everything looks like it's just one file, but this file can contain many complex objects inside. So what this does is it allows users to choose the best method without really modifying the source code at all. And it means that I can write code that has some coupling to visualization. I could run, use files, get that working, then run both of them during the simulation, and then it immediately runs like it was fully coupled in memory. So you don't use the file system. So what's nice is, then users don't worry about all these, and that allows us to generally get such high levels of performance. There's very little tuning, in other words, that you'll do, and Norbert will go over some of that, but there's very little. And for developers, it's nice because you can do things and not worry about so much of what's inside of ADIOS. You can just be very isolated. So let me just continue and say that, again, there are some performance numbers. This is part of the WDM ECP app. These are 2 different fusion codes. And what you can see is that if you're going to write on Summit and just wanted to write in the NVMe for temporary storage, you can get over 36 terabytes per second of throughput. And GTC, and showing here going to GPFS, and you can get like 2.2 terabytes per second. And these are just ways of, this is like a parameter tuning that you do. And what you see on the left is this is the majority of the APIs you need to learn. And we'll teach you these later, but if you can understand, there's an open, there's a close, and then for all the data that you want to put together into what's called a step, so it can be like for an experiment, like a certain amount of time, say for every millisecond data is collected, we'll call that a step. And put is, think of it as for each variable. So this is just you're going to put. And similarly, you can see for reading, instead of a put, there's a get. And also this is like inquiring the variable because it's self-describing data. And if you can learn that, then you know the majority of the APIs you need to know in order to use Adios. Here are some different performance numbers. And again, you can see who's the contact for the various, in this case, ECP project. This is actually showing XGC. The author is CS Chang from PPL, who's the co-deputy for the WDM app. You can go to their GitHub page. And the thing that we'll say is that when we were doing the strong coupling with the gene code with XGC, that what you'll see is that the time spent in the coupling, or the overhead, when you look at how much time compared to wall clock time, we're down to 10 to minus 6 seconds, which is basically who cares. And then this is work we did with Mark Taylor's project. There's also usage from Peter Thornton and from the stream part, which is part of E3SM. And some of this data was provided by Jayesh from Argonne, where you can see that the performance of Adios here greatly reduced the time when they ran with their new I case. And for Scream, again, they found a 4 to 5x improvement in IO when they have the terabytes of data. Certainly, and again, I think you saw even the newer graphs than what we have here with the WarpX code, where we can achieve now over a terabyte per second for the IO bandwidth. There's cases with MWChem of where what we did was say, rather than just going in your code and they would sort their atoms and then write this, could we use Adios and its staging capability to do more? So go and do more. Sort, run a principal component analysis, run a visualization. And when you do that, what you'll see is that you can actually make the time almost comparable to doing no IO. In other words, 386 seconds running NWChem originally in this case. And this is one of the, I think it was one of the COVID molecules that we were running. But you can see that we can actually run with sorting, with PCA, and it's very low extra time compared to no IO, and certainly much less than just running and getting this sort of data. We also did a lot of work with Candle, and this is some of their deep learning ways. And what we did was look at ways using Adios for asynchronous collection of the results for the training. So it allowed for continuous simulation running and training. This is a 17.5x more efficient workflow running on Summit, and you can see the contact. Similarly for seismology with the spec FEM 3D code, this has huge amounts of data in small wall clock times. And in their case, again, we were able to accelerate their IO by many orders of magnitude so that Adios became part of your own project for the adaptable seismic data format. And this was actually really good. It's a very exciting project. This is showing one of the highlights along with 3 very recent papers that were all in physics of plasma. Julian, Gabrielli, and Juni were part of, this was XGC, Gene, and Gem. And this was all the coupling of these codes. And we show these complex workflows which have more coupled from visualization using VTKM services to performance monitoring with TAL. And in all these measurements, what we'll say is that what we saw was that in the ECP review for the WDM project, you can see that the time spent in coupling is so insignificant. So our goal here was the code that's expensive, in this case, XGC, we don't want it to wait. So the coupling was really meant to say, The expensive code, don't wait. The code that's a lot cheaper, it's okay if it waits. We were really looking at codes which are not going to run in exactly the same amount of time and certainly not in the same resources. This is showing a bit more detail on some of the results with seismology. And the point is that, I mean, you know, this is not that long ago, but still 7.5 petabytes done in a single workflow step, which I believe was just in a few hours on Summit. That's a lot of data, and that means you have to do things very efficiently. And you can see that the times that were spent between no IO and writing ADIOS BP4 files, you know, it's not that significant. And these were all sorts of the additions that we've done. So again, when you look at the amount of data, you can see that, you know, IO has to be very fast. A terabyte per second doesn't cut it anymore. This is some more work that we did with both C.S. Chang and Michael Churchill. And what this describes is that we have an fusion reactor in Korea. And the point was to use ADIOS, and it just streams the data. I believe we stream every millisecond from these very fast ECI cameras. And we stream the data. And as on this highlight slide that was submitted by Michael, it talks about, you know, being able to go from 12 hours going down to 10 minutes when you do the streaming. So the hope is to be able to use this technology in conjunction with AI in order to reduce the time spent in your workflow. In GTC, when we found out what we were doing and we started to really optimize the IO further, you can see a code that was spent in so much IO, we can greatly reduce the IO time from 1288 seconds to 606 seconds. And these are fairly typical at times that we see from IO optimizations. And if you do have a question, I hope, again, my colleague Norbert can monitor the chat window. Let me go over to the LAMPS code. One of the guys in our group, Li-Ping Wan, who also worked with WarpX, he worked with LAMPS, and they have a module. You can go into the GitHub page for LAMPS, and you can actually use ADIOS. And if you look at their default IO behavior on Summit, up to 512 nodes compared to ADIOS time, you can see in the throughput, you can see over a terabyte per second, and you can see numbers which are much, much less. This was some of the WarpX results again that we've showed. And the original thing was we need to improve the writing capability, but it came not just improve that, we said we need to improve the reading, and that's the story Jean-Luc said. This was part of the E3SM page. And again, this is just part of the page they had. And, you know, again, I'll pause and saying, there's not a lot of secrets in ADIOS, but by working with E3SM, one of the things that we saw was that there's a huge amount that was done for the IO with the feeling that the data has to be written a particular way. And for a lot of the optimizations done to use ADIOS, it's then breaking down all these, I have to do this aggregation or I have to do this. And by breaking down that, you can remove a huge amount of the time spent in IO. And that's what these cases are really showing along the way. As I mentioned, the SKA project, I mean, this is exciting because many years ago, one of my friends asked me, you know, to go down to the supercomputing center in Perth and give a talk. And I spoke to one of the astronomy professors, Andreas Wischnick, and, you know, he told me that he was looking at, you know, all the different IO solutions. And for radio astronomy, of course, these things need to last a long time. The data needs to last like forever. So we went over a lot. One of his PhD students then started to work They wrote several papers with us. And eventually then the student came over and is now full-time staff at Oak Ridge, but still works part-time with these guys, meaning this is his night job. And he decided to write a paper and became a Gordon Bell finalist with the SKA team. So this is a video, which if someone could just say, or just put in the chat window that you can hear it. I'm going to play the video. Turn your volume up.
Hello, everybody. In this
It stopped playing.
short presentation, I will show how we've integrated ADIOS II to enable scale processing. My name is Andreas Witzenetz, and I'm presenting on behalf of the ICRA Data Intensive Astronomy team and the Gordon Bell Prize finalist team. ICRA is the International Center for Radio Astronomy Research in Western Australia. Let me first introduce the Square Kilometer Array. The SK will be one of the few mega science projects of this century. It will consist of 2 radio telescopes, one in Australia, a low frequency telescope, and one in Western and South Africa, a mid frequency telescope. The headquarters will be based in the UK. Phase 1 will realize about 10% of the full SK by 2028. And the Phase 1 science books consisted of 2 volumes, more than 2,000 pages, 135 chapters, and more than 1,200 authors from 31 countries. Currently, there are 50 member countries in the intergovernmental organization. Construction will begin mid of 2021. In this presentation, I will focus on ADIOS II integration. The SKA scale data flow poses a lot of data I/O challenges. Current radio astronomy data processing is mostly consisting of single machines or small clusters nowadays. The backbone of the radio astronomy software is CASA-Core, so 560,000 lines of code developed over many decades. Up to now, it only supported serial I/O. The measurement set data model, which is underlying this whole reduction system, is based on the so-called CASA-Core data table system and produces tens of files for a table. And that, at the end, will produce millions of files for typical SK observations, potentially up to 100 million files for typical SK2 observation, and means a huge pressure on shared file systems, metadata management systems, and archiving systems. The table on top right shows a comparison between current day radio telescopes and the SK1 low. And the lower part shows a depiction of the CDTS. The ADIOS storage manager is trying to parallelize the column layer I/O for CASA-Core table data system. Initially, in 2014, we started preliminary research, which was performed to determine the optical storage backend for parallel I/O for large-scale astronomy data. At that point, ADIOS was selected, and in 2015, a storage manager plugin was designed for the CASA-Core table data system based on ADIOS. That initial implementation achieved parallel I/O at the column layer, mapped the column-based data structure onto variable-based storage backends, and implemented prefetching for table reading. But it was still not on the table layer. The table layer was still serial, and random access was not fully optimized. As you can see, the scalability of the system was already quite nice, and is seen on the plot on the right. In 2018, ADIOS was rewritten from scratch as version 2.0, and we took that opportunity also to re-implement the TDS for astronomy data. That also optimized some other things like a table engine aggregation for small random write operations based on 0MQ. In 2019, the Kaiser core table data system was refined to allow table layer parallel I/O. So that's on the Kaiser core layer, not on the ADIOS layer. And it was also expanded to from 32-bit to 64-bit to remove the 32-bit limitation for writing very large SK observations. And both of these implementations were optimized to full-scale SK simulations. We've then put that onto the Golden Bell Prize and went to be a finalist at the end in 2020. And yeah, the key figures of that run on Summit. So 3 hours of runtime almost on the whole Summit computer. That was about 2 times faster than actual SK in terms of data rates. We've produced 27,360 channels instead of the 64K channels for the SK. Produced about 33 billion visibilities a second. That represents 2.6 petabytes of total data flow. The output of the initial ingest was about 112 terabytes and 760 file sets after heavy averaging. And that represents 11 gigabytes per second sustained write rate. That's not a limitation of ADIOS II or anything like that. It's actually the way the processing runs. And we have achieved about a terabyte a second on subsequent runs. Altogether, we have written about 500 trillion visibilities during the whole run. Visibilities are just complex numbers, essentially. And the final image cube after the second stage reduction is only 3.1 gigabytes. So that's an extreme reduction of the data. And that's my.
Okay, so thank you. And I'll be, again saying, work that we did with WarpX, I think it was great. Axel covered it, so I don't have to say anything about that other than it's not just about writing. There's so much in terms of reading. And the thing that you should see a lot of times is if you're going to read your entire data set, what scientists running with Python sometimes don't remember is that, this is a system which has 32 cores per node, or per process, I should say. So just running with all the cores, all of a sudden you can go from things which are logic contiguous, which is most of the file formats that down to what ADIOS does. And you can get an extreme performance improvement for your reading. So what you can do is you can really remove the IO bottleneck as well as the time to process the data. So ADIOS is really designed for things at scale. In this case, for reading, think of what we're saying is on like 4 processors with 32 cores per process. This is one more movie which just tries to show you where, well, I guess this just shows you. And what we're saying is you can launch these MPI applications, and this is just running a Gray-Scott reaction diffusion equation. And later on, you can just run analysis. This is a PDF analysis, plotting codes to do matplotlib. You can launch Visit in order to just, what you think is you're opening up a file, but everything is in memory. So there's actually no files that are being done. And what we say that when you're doing all of these in situ is we think in situ should have this twist of where what you can do is you can think of pausing the visualization, even changing the visualization if you wanted, or quitting. And as you quit, you'll see that you can still run the simulation. Everything runs. This was run on a virtual machine for a tutorial, and this is one that we give you to run. But if you're running off of a system which has just a few nodes, you'll see things don't stop. So what we're saying is, imagine you have your simulation, and since it's doing this pub subscribe system, you can just launch a visualization system. It can just subscribe to some of the data that was going to the file system, and now you'll have in situ visualization. Let me just go in saying, if you have no questions, next up, what we're going to do is we're going to switch. Norbert Podorsky is going to tell you a bit more about some of the details now of how to run with ADIOS. I'm going to stop sharing. Norbert, it's now your turn. Norbert, you're muted.
Yeah, sorry. I just started my presentation and it hit everything else. Okay, let me share. Okay, so I'm going to talk about the details of the ADIOS API, and that will take a while, and then we will dive into the question of how to scale ADIOS I/O. So I will also tell you all the tricks that this application that Scott pointed to are using at large scale. Just a moment, Scott. I have to turn on the pointer, right?
Yes, Norbert.
Right. So Scott showed you already the links, and you can download this PDF. Just repeat again, the API is declarative in the sense that in the user code, every process describes what data they have or what data they need in a given step to write or read. And then everything else is separated from the user code. So all the selection, the choices for doing the I/O is selected at runtime. So the basic concepts of ADIOS are the following. The self-describing data is one of them. Self-describing for us means that when you get a data set, you can open it with tools and see the content, and you can read arbitrary pieces of that data without doing anything magical, and you don't need notebooks from other users to know how to access the data. It doesn't mean you would understand what a specific variable means without knowing the science behind it. And then data is contained in variables, which are either single values or multidimensional fixed type distributed arrays. And then there are attributes that are static labels, information for humans or machines later for processing that you assign to those variables. For example, a data set looks like this. It has a set of variables, and the variables have a name, which looks like a path, so that you can organize logically in a hierarchy, but it's just a set of variables. Each of them has a type that you can see on the left side, and then it has dimensions, either single values like scalars, or a one-dimensional array, or a three-dimensional array with a given size. In ADIOS, we also usually have minimum and maximum values on that array ready in the metadata of that data set, and that's it. And the n-dimensional arrays it has a shape which is basically the size in n dimensions. It has a fixed types, and then it's composed by multiple processes. So every process has some data to contribute into this global array. They have something in the memory, and then they add that to the global array, describing its starting position and the size in the local memory to add it. So that's that's what an array is. It's not limited to every process creating one block. You can create a global array by each producer writing multiple blocks in different places in the global array, or some process may not write at some point. You may have big gaps in the global array so that you don't completely fill up the global array. In ADIOS, we don't store the white spaces, so you can create arbitrarily big global dimensions for your purpose. And the blocks can also overlap each other, which usually is a bug, but you might want this. If you have data overlapping across processes, you can fill up a global array with data, and then you will get some value, one of those values back when you read. Okay, so the second concept, and this is a very important concept, and it's nowhere else, so I have to explain this carefully. Is this the step? So in our publish subscribe concept, what we mean by is that the producer is producing steps. The step consists of a bunch of variables and the attributes assigned to those variables. All the data is consists a step, and that step is produced. Now, a consumer can get access to that step and then read the content of that step. I mean, whatever piece it wants from that step, not the entire step. And then the producer code produces steps over time. So we organize in the API, we organize the data input and output in steps, and that will allow us to make staging and file I/O very similar to each other. So I must emphasize that the step is an ADIOS concept. It's not necessarily tied to the time steps concept of your application. Usually, what it means, if you have application time steps, you produce ADIOS steps in a loop somewhere every now and then in time steps, but it's not tied to that. The rule is that the entire content of a step is either completely written or not at all. And a reader will get access to a content of the step either completely or not at all. A new step can be completely different from the previous step. So there are no rules to keep everything the same. In this tutorial, and as we show, and usually you define your set of variables well ahead of the whole I/O, and then every step has the same set of variables, but it can be a completely different set of variables. And the array sizes can change, and array decompositions can change every single step. But every engine of the ADIOS implementation must guarantee that a consumer, when it gets access to a step, then all the data is available as long as the consumer is holding to it. This is very important for staging. Of course, in a file environment, the data is always available. And one strict rule in the ADIOS design is that the entire content of a step must fit into the producer's memory as a copy. So when you write your application, you are limited on devising what a step means, is that it must fit into the memory. And so you may have to chop up your step if that is not the case. Okay, so the coding basics. ADIOS is written in C++, and so naturally we think about objects. The main object is the ADIOS object. This is just the placeholder, the parent of every other object. Then for every array or every scalars, you create a variable object. And then you can create attributes that are basically constant labels assigned to variables or assigned to the data set. The I/O group is that is related to this step. It holds all the variables and attributes for that will be contained in that one step, and then also the settings for the runtime settings for what will happen at output or input. And then the engine object is the one which will take care of the data movement. So that there are file-based engines and there are staging engines. And finally, we have operators, that ones that are working on the data on the fly, do something like each compression algorithm is implemented as an operator. So at the first step, you have to create an ADIOS object. You pass an MPI communicator and a config file. Both are optional. In a serial code, you don't have MPI communicator. And the config file is there to provide the runtime parameters for an application. But you can omit these and you can encode stuff in the source code too. Next, you create an IO object. So for example, in this first example, how do we create a checkpoint checkpoint file? So you declare an IO, you give a name. The name is not important unless you have a config file. Then you refer to by this name to these IO settings in the config file. That's the only purpose for the name. And then a variable is an n-dimensional typed global array. It has a shape, which is the dimensions, the global dimensions in the space. You define a type, you define the type, and then you define a name. This is the name, how it shows up in the output. So it's just a single character name in this case. You can add the full pass with slashes. It's all logical, so you can use whatever you want for separators. And then on every process, you declare these variables and you provide the local offset and the local size on that given process. For simplicity, we decided that in the C, C++, Python API now, there's always a row major representation of variables. In Fortran, MATLAB, and R, it's always column major. And so you don't need to worry about if someone is producing a C++ code is producing data and you read it in Fortran, the dimensions will show up flipped and you don't need to worry about these row major, column major discrepancy. Similarly, the data records if it's big endian or little endian, and if you read it on a different architecture, it will convert the data automatically. Okay, so if you have the IO object, this is how you write a checkpoint which consists of a single variable. You create an engine and you give a name. This name becomes the file name if you use a file engine. If it's a staging engine, it's the reference name how the consumers will be able to find this stream. And then you call put on each variable that was declared, and you provide a data pointer which contains the data in the application. And then you do close. So this open, put, close, this is the pattern for a single step output. If you have multiple variables, you have multiple put lines here. For attributes, you don't need to do anything because they will be automatically added to the output. The one important note here, put doesn't do anything by definition. It's the close will access the data pointer, so you should not change the the content or invalidate this pointer before close is executed. So that's all the output step. On the reading side, it's very similar. You declare the IO, you use a name. Again, is only important for if you have a config file. And then you open an engine with using the name and the read mode. And then you can create a variable object by inquiring the IO objects. So here we assume you know that there is a T double array in the file. If you don't know that, there is other functions to list the variables and discover the types if you want to do a generic coding. And then you allocate data. There are other functions to discover the global shape. You can do your decomposition in the reading code. You can allocate data on every process what you want to read, and then you do call a get and pass this variable object and the pointer where you want to read in the data, and then you call close. And you have so if you have multiple variables, you have multiple gets. So I hope if this is clear to everyone. If not, please type it in the chat, and hopefully Scott is monitoring it and can answer. Okay, so when Scott showed some charts where big applications wrote to the local SSDs and NVRAMs in the Argonne machine and the Oak Ridge machine, there was no change to this. Even though those are local files, ADIOS files are organized in a way that it can be put into this distributed file system, and so it just works without any changes. Okay, so now for analysis and visualization, what usually happens is that you don't just have a single output. You have a series of outputs. And so what do we need to do here? This example is really not different from the previous one. It just shows some code saying how you can set your engine if it's what the analysis data was not declared by the user in the config file. And here we use a nicer temperature string for the name of the variable. And then we add an attribute, a string label, which has the name unit, and the value is Celsius to the temperature variable. So later in the data set, it shows up as a string attribute, and then you can even list the value quickly. And if you want to read it step by step, so you open once, and then you call begin step every time you want to access one step, and then you call the put functions, and then do end step. So in this case, you have multiple puts in one step. You have a begin step, end step pair for every step, and then you have open, close once for the entire application. Okay, so I have to explain the put function because this is the single most dangerous function or concept that we added, and most of the bugs originate from here. So what we decided long ago is that the engine put function works in a deferred mode. So put, a variable object, a pointer, and mode deferred. This means that put simply gives Adios a pointer to remember to do I/O with in end step. And that means the application must not invalidate this pointer. It must not change the content of this this pointer. In most cases, the I/O is simple, right? You decide you do some output, and then you start giving the pointers. These are my variables, and then I do the I/O. Done. So it doesn't cause any problem. But sometimes when the I/O is constructed in subroutine calls and pointers are allocated temporarily to do some I/O, this can lead to the problem is that the pointer becomes invalidated before it's actually used in the I/O. So there is the sync mode where you can explicitly say that copy this content of this pointer, this user pointer, and then so that the application can change it. So the sync mode will force any Adios engine to take care of the data, to save it somewhere, make sure that if it's lost, I mean, if the user pointer is lost, it doesn't affect the I/O anymore. So because the default is the deferred mode, and someone looking at the example sees engine put, naturally, people, even the Adios developers writing examples, assume that this is done. When you're done with the put, you are done with the pointer, but it's not. Okay, so now if you have a configuration file, and by default, we are writing an Adios output file, but for some reason you want an HDF5 file, then you just change the engine name, engine type to HDF5. And that means when you run the code, the application, and reads this configuration file, it will use the HDF5 engine. Is an engine in Adios that uses the HDF5 API and HDF5 library to produce an HDF5 file. Or in the source code, you can call set engine before the open call. Okay, so that was the C++ API. In Python, there are two APIs. One is mirroring all the C++ functions with the same signature, so you can write full-fledged applications if you desire so. But there is a simpler version, a high-level API, which is tailored for easy reading of data. So the requirements are NumPy and MPI for Pi, for parallel Python, MPI for Pi, for sequential only NumPy to read in write or read in an array. So then you have basic functions open and close. open, you have a file name and read mode, write mode, optionally communicator, the configuration file, and that string of the IO object name that's used in the XML file. So once you open a file for reading, you can list the variable, the available variables. Function returns a dictionary that you can print out, and it looks like on the right side we have t and delta t here with the two-dimensional variables with a given shape, 10 by 16, only 2 steps. Min max is 0 and 200. And then if you want to read it, you can just say read t. That means it reads the first step, the entire global array. But then you can specify a subset of that array, and you can specify steps from which step and how many steps you want to read in. So the last example would read in the entire 2 steps and 2-dimensional array as a 3D NumPy array in a single process. But so if you do in parallel, you need to do decomposition and use start and count to divide your reading pattern. And there is another construct in Python, is the for step in the file IO handle. This construct will step through the entire file or the stream. And in that loop, you have access to all the variables in a given step, and you can read those. So if you will look at the Python code in the example later that I'm showing, this is all it takes to add a Python analysis or visualization script into an audio stream. So this is able to use the streaming engines and get the data directly from an application and read it step by step. Okay, so our example is today. Now I'm not doing hands-on, but I'm just going through the slides in case later you want to do the hands-on yourself. So all the examples and codes are available online. We have an ADIOS II examples repository on GitHub, and the Grayscale example is one of the codes.
Norbert?
And, yes?
Can you just mention quickly, there's a question about the Fortran API. You would have to go into the hidden slides.
Right.
But you could probably just quickly do that.
I cannot do that. I don't have a presentation. But so, unfortunately, I don't see the Zoom window either.
Just mention it then, and
if you download the slides, you can see there is also a Fortran API, a set of slides on the Fortran API, but we hid it for this talk. So I'm sorry, I really cannot see the question. But I have to stop my presentation if I want to see the question. What is the specific question, Scott? Okay. Well, okay, so let's continue then. So in a tutorial, when we do a hands-on, we pick this Grayscale application to show all the functions of ADIOS and everything that we can do, from just writing files to doing in situ visualization. So in the example, we run the code in a 3D decomposition, but run on only 4 processes, do a 2D decomposition. But so anyway, we write data in a certain decomposition. Then we run analysis, reading data with a different decomposition. And then we run visualization, which only visualizes one slice, one 2D slice in one process. But if we run in multiple processes, then we get different slices. And use this pipeline to showcase how it works with ADIOS BP files, HDFI files, and using SST to do staging. If you build that application, you need Python with NumPy, MPI for Py, and Matplotlib to be able to run the the Python plotting. You only need C++ compiler ADIOS build for running the writer and the reader. So when we run the application, it produces an output step regularly, like every 10 steps, it writes an output step. And then the reader can read these in step by step. It's written by the analysis code is written with this concept, reading the data step by step. If you only care about file I/O, never care about staging, you can also write a code that opens a file and sees all the steps already at once, and you read whatever you please. So that's really limited to handling a file. If you want to write analysis codes that has a potential to go in situ, you need to read the data step by step. Okay, so if you run this Gray-Scott example, we have a 64 cube output here, and if you run it, you will find a Gray-Scott.bp output file. Okay. Then you can use the BPLS tool to list the content. This works on ADIOS BP and HDF5 files. So this is the Gray-Scott example. The two big data, the 3D arrays are U and V, and this means in this example means we have 100 output steps, 64 cubes data, and the total global minimum and maximum is these values on this array. And then we have some attributes saved that they were the input parameters to this example. If in case you want, if you are interested, you can print out the decomposition, each process start and count offsets, how this 3D array was decomposed. This is useful when you develop your applications and you want to make sure that your decomposition fully covers your array and you have no overlaps or no gaps, and it really works as intended. And then with BPLS, you can read arbitrary selections in the data. So reading a 2 by 2 by 2 cube in the center needs these parameters, the start and count, using 4 values. First one is the time, and the next 3 is the three offsets in the middle, and then the size is 2 by 2 by 2, and then you can just get this data. Yeah, and so BPLS is useful to read any portion of your data and then print it out on the screen if you want to. Okay, so now if you have a XML file for configuration, all it takes is to change the engine type. So in the Gray-Scott example, you will find if the file looks like this. It has 2 I/O groups, simulation output and the PDF analysis output. The simulation output is used by Gray-Scott to produce the output data, and the default engine type is BP4. You can just call it file stream, and that will produce the same thing. And then it has some parameters. Changing this to HDF5, the simulation output, and then you run the code, you don't recompile the code, you don't change anything in the code, the result will be a gs.h5 HDF5 file. So you can list the content with HDF5. And you see our structure is creating a new step in the hierarchy of HDF5 every single step. And then you can use BPLS to read from BP or HDF5 file in the same way. Okay. And then the next step in the application is that you run the analysis code. This will read in the gs.bp file, and then it produces another one, and will create PDF calculations on every single 2D slice of the 3D array. So that then you can use the PDF plot Python script to create this 1D plots on the different slides. Or you can run gsplot on the gs.bp file or gs.h5 file and create these 2D plots. Okay, so that was all about the APIs and how ADIOS works. Unfortunately, I will stop sharing so that I can see comments. Oh, someone put the entire Fortran IO here.
Norbert, that was me. There's no other questions.
Right, okay, so the which standard is Fortran 90. So the answer to the question, it was Fortran 90. So we don't have a Fortran 77 API. Okay, let me go back then sharing. Okay, so let's talk about how do we scale ADIOS on the big computers. And that's basically, we try to make ADIOS as easy to use as possible. It's one of our goals is to make it easy to use. And that is basically, there are two options in ADIOS to change the behavior for addressing file I/O on the big computers. One is the aggregation. So ADIOS saves the data in multiple files. It presents, for reading, it presents as a one data set. So you don't need to deal with multiple files. They are in a subdirectory, and you can read whatever you want, no matter how many files we are using. Sorry, Scott, did you say something?
No, go ahead, please.
Okay. But we use number of files to maximize the file system bandwidth. And the other one is appending multiple steps into a single output. If you think that's controversial, you are right. So if you were afraid of using that, we understand that, and we are doing everything we can to make this as a safe option, but it has great savings after you do aggregation right. And beyond all that, is really just picking your engine on a given system that gives you the best performance. So let me explain these things. So basically, the two natural choices for users who do I/O is to create a single file and try to write from every process into that single file, or create one file per process. So create a big flood of many files on the file system, and every process writes its own, which is very fast until you choke the metadata server of the file system, and everything collapses or slows down very much. So none of them is a good solution for scaling up I/O. What is necessary is to pick a number of files which is proportional to the file system capability. It's independent from the number of writers. In case of ADIOS, you can't have more files than writers. So if you have few writers, then you won't get big performance. But for scalability, what we mean is that the number of files have to be picked to address that file system that you are writing to, and not how many processes you have. And so in the ADIOS BP engine, you pick the number of aggregators. Like 2048 is a good big number on Summit at LCF, and at Oak Ridge, but it might be much less in a different system. Aggregation ratio is basically the same. Is a divisor to how many processes should aggregate into a single file. So it's just two different ways of picking your number of subfiles. The ADIOS default settings, if you don't say anything, since 2.6 is one file per compute node. Basically one file per shared memory, all the processes who share a memory. And that's a good number for scaling up. It's not the best at medium scale, but it's very good for large scale runs. So one example is we worked with the vPeak IO test on Summit, and this is a CPU code. So we were running up to 42 processes on the each node, and we were looking at how many subfiles gives us the best I/O performance. And you can see as the number of nodes, as the application grows, it's a different setup which is the best. The blue one is when every process opens a separate file and writes a file. So here we have 42 output files, here we have 84 output files. We can get to about 600 gigabytes a second on 84 nodes. But then if we double the size of the application, this is not performing anymore better because we are creating too many files already. So actually using Aggregation Ratio 2 and writing only half of the number of files, every 2 processes writing into the same file, then we get to 1 terabyte a second. But then again, if we double the number of nodes to the run and the number of processes, this is again too much, and basically cutting down every 7 times. So just creating 6 files per node, like 1 file per GPU, gives us the best performance. And similarly, if you look at the applications that are using Summit at very large scale with lots of data, you can see that the practical aggregation ratio is keeping the number of files around 3,000 or less based on needs. If you go over these on Summit, then the file system starts to suffer from just creation of too many files and handling too many files, and the performance will drop. If you go below these, then you are not utilizing the entire file bandwidth on a given number of processes. So aggregation is our one big knob to tune the I/O, and this has to be selected carefully. And then if that's done right, then what's surprising on running on these large scale systems with lots of processes, if you do I/O regularly, like here the XGC code, writing these F0 analyzes data out every single output steps. This is for analysis. They want this data as frequently as possible. But if we just start creating a new output data set on the increasing number of nodes, there is a point here on 1,000 nodes where things start to break down. This takes too much time, and we looked at it. The reason behind this is only spending the time of creating the new files. So things break down at scale, and even though we use proper aggregation, which is good I/O for if you have a lot of data and you want to write out at once, but here we have like 40 gigabyte data every step, and writing 100 steps over 20 minutes on a 20-minute simulation, it takes a lot of time just to create the files. So instead, it's much better to create a single output in the beginning of the run and just append all the 100 output steps into that same single output file. And then you can see that the time is around very similar on every number of nodes. This is a strong scaling test, so the data size is the same no matter what the number of processes is. The data size is related to the setup, not to the number of processes. This is a corner case, but I picked it because it really shows you how bad things get when you go up in scale, both in frequency of output and the number of processes. You will hit this limit even if you do aggregation properly. So these are the two things that the applications need to use to have good performance in this over 1 terabyte per second sustained performance on Summit. So GTC is another code, and it was not, the big deal was not about improving the checkpoint and writing more than 2.5 terabyte, 2.2 terabyte a second, the checkpoint. It was more important that we decrease the number of files created over the long simulation as like 32,000 analysis data into 512 files. and the single snapshot files that is a smallish data written every single step, we decreased it in the single file. So Scott showed these results, decreasing the I/O from like 30% into a negligible overhead. The big story behind this is that the GTC people worked very hard over years to improve to rework the GPU computations, and they achieved like 20x or more than 20x improvement on Summit. So the total computation time went down 20x, and that meant that the I/O overhead became dominant in the application runs. But using Adios, this can be eliminated, and one part is writing the big data with proper aggregation. The other one is keeping the number of files small over the course of the runtime. And the same story was with WarpX that you could hear today on the in the morning. So just using Adios instead of the original plot file in the AMRX library didn't change much at scale, simply because the AMRX plot file is using the same tricks. It aggregates to a number of files, and so it has the similar capabilities that Adios by default. But appending all the steps together, we got much better performance for a long run. And then doing the aggregation properly, we could sustain over a terabyte a second when we went over 1,000, 2,000 nodes. So these are the two things that the applications had to watch out for, to not to ruin their I/O performance on this particular machine, right? And the one more typical, not typical, but still there are lots of applications that think if they have small amount of data, it's better to aggregate it on rank 0 and then just write it out on a single process. It's certainly convenient to program it, but I would argue that it's not more convenient than every process. You just declare what data you have, what small data you have, and then let Adios gather that data and write it out in parallel. And so two stories was, Scott already showed this. In WChem, what people have to do is like write every 100 step to keep the I/O costs low. So they cannot just output as much as they wish for their analysis simply because the I/O cost is too much. But adding Adios into the picture, they can easily do that because the data is not that big. It can be aggregated, sorted, and write to a file system very fast. And similarly, as Scott said, LAMPS is the same story. With doing I/O in parallel will pay off at scale. So that was my part of the presentation. And do you have any questions? So do you have any questions? Do you guys have any question about scaling up Adios on any machines?
So why don't we continue, Anna? We hope you make it.
We are skipping the break.
There is no break.
There is no break.
In the
Nope,
slides,
there's no break. That was a mistake, not a break.
all right.
This was the break. Okay.
All
There
right.
is a question. What's the benefit of deferred mode in the put method? Okay.
Right. So yes. So it's hard to explain, and it's because it really depends on which engine is doing it. And to be honest, as of today, they don't have too much benefit because how the engines implement the API. So there is the API as a concept, and there is all the engines that follow the rules. The deferred mode means, well, still there is the BP file format the BP engine can avoid allocating memory until to the end step. And at that time, if you use everything by deferred mode, it knows all the data that goes out into that step and can do memory allocation at once, which can be very much faster than if you have lots of variables in a step and reallocate the memory, and potentially you have to shuffle data around. So there is a potential there if you have lots of variables, and then if you do everything with sync mode, then you can run into that your IO bottleneck will become memory reallocations and shuffling, nothing to do with the file IO. And so we had such complaints in one application, particularly because they had so many variables.
Okay, there's one more question. Can we use any in situ visualization tool of our choice with ADIOS?
Well, so the answer is certainly yes, as long as the choice of your in situ visualization tool talks ADIOS. ADIOS is for moving the data from producers to consumers. So if a visualization tool is able to talk with the ADIOS API, then it can connect to any ADIOS output and read it back.
So Norbert, let me answer it differently. We work, I mean, Kitware is a partner in our project. We have Visit developers part of our team. So peer review developers, Visit developers. So in terms of things like Visit and peer review, the answer is yes, yes. I mean, it has to make sure you have to compile it with ADIOS, and if it is, then it will work. We do a lot with matplotlib with Python and visualization codes for simple plotting, so they all work. So as long as the APIs for reading are in there, then it will work. And speaking of that, Anna is going to start talking, and Anna, you're going, okay.
All right, so we are going to cover the algorithms inside ADIOS that can do in situ analysis, but first I will be talking about data compression. As before, ask your questions in the chat, and then Scott and Norbert can read them, because apparently in Zoom you cannot see the comments and the slides. All right, so ADIOS supports operators as a mechanism for performing calculations on the data before it is written by an engine. A general purpose operator provides the user the ability to perform whatever calculation and manipulations, well, a large set of calculations to the data inside the engine. The user can swap operators in and out at runtime, so it's very flexible depending on what you want to do with your data. And it's plug-in based, so you just define the operation that you want to happen, and then ADIOS is gonna apply it on the data, and then when you read it, ADIOS can take care of undoing it, like in the case of compression. Data compression is provided in ADIOS using this mechanism. So it uses operators. It provides support for a number of different lossless and lossy compression methods. And we are going to look at some examples. Enable compression requires minimal development effort for users. So you just simply specify an operator for each variable. And this enables ADIOS to automatically compress or decompress at the point of data publication of subscription. So ADIOS supports lossless compression such as bzip2, in which case we preserve every bit of the data, but usually the compression rates observed in practice are minimal. So ADIOS also supports lossy compressors like mGuard or SS or SVP that provide much higher compression rates usually more than an order of magnitude compared to the lossless methods. But obviously, information is lost. It's a lossy compression method. However, most of these methods allow control of the loss through parameters, and those can also be easily set in ADIOS. One of the compressors that is supported by ADIOS, mGuard, can consider relevant quantities of interest inside your data, and then they can reduce the data so as to preserve those quantities. The examples that we're going to look at are designed so they apply to every type of lossless compression, but some of the algorithms might have other parameters that you will be able to tune. Another type of operator that you can apply is converting from different types. For example, converting your data from double to float. So the users can apply different operators to the variables in an IO group, and we are going to look at to see how this is done. So there are basically two concepts in ADIOS that you need to know. One is how you define the operator by giving it a name and a type. And then for each variable that you're declaring, you can use the add operational function to add an operator to a given variable. So if we look at the example that's on the bottom of the slide, you declare an IO group. And then in this case, we declare two variables, a float and a double arrays. We define an operator. In this case, it's an SFP compression method. We give it a name, and the type is the one that is recognized by ADIOS. And then for each variable, we can add this operator. And next to the operator, we can give the parameters that the operator can understand. So for compression, all the compression methods can have an accuracy as a parameter. So we define the parameter, and then we use ADIOS as we normally would. So you open the IO, and then you write the variables or read the variables. You can also use an ADIOS XML configuration file to define this. And you've seen some examples, Norbert showed them. So you select the engine for writing, and this can be BP4, SSD, in situ MPI, dataman, SSE, and we're going to cover what these engines do and what's the difference between them. But all of them support compression, so you can choose any of these engines. HDF5 does not. And then you define your operator, and you attach this operator to some of the variables that you define in the XML file. And we're going to see the example by looking at Gray Scott. So this is where the hands-on part would start. If you would like to do this afterwards, I think it's worthwhile. Look at the Gray Scott example. And then inside Gray Scott, you're going to see how some IO groups are defined. In this case, is the PDF analysis code that uses BP4 for data management. And then it defines the variable that it's going to use. And inside each variable, you can define operations. In this case, we have a compression, Ssd compression, so lossy compression with an accuracy of this given value. If this was a hands-on, you would have a task right now. So looking at the Gray Scott example, you want to modify the ADIOS configuration file so that you use the BP4 file engine and then run the PDF analysis application with dumping the input data while compressing the two main variables that are used by this algorithm, so U and V. And in this example, you want to use lossy compression method SZ with different accuracy level just to see how the total file size changes. And in order to see the difference, you want to compare what you would get without compression with the new BP file. And we are not going to wait for anybody to try to do this. I'm going to show you what you will see. So the first command you've seen this before on Norbert's slide. So this runs Gray Scott. It's a 64 by 64 by 64 cube size. You get a BP file in the end. It's called GSBP. And if you look at the size of this file, in this case, it's going to be 401 megabytes. If you run with the new configuration file where you use compression, if we look at the second command that so you look at the size of every BP file that is generated. The initial one, the Gray Scott BP, is the one without compression, and it has 401 megabytes. And then the new one, the PDF that you generate with compression, is much lower, so it's 25. Then you can use BPLS as before to look to see what's inside each folder. And as you can see, UV is present in both folders, both BP folders. The second one, however, is compressed. You do not see it here because BPLS decompresses it for you and shows you what the data is inside. But if we inspect the values, so here we look at the values of U and V, well, in this case, only of U inside each folder, we can see that there is a difference between them because one has been compressed. I will be moving on to in situ engines. So if there are any questions about compression, this is the time to ask them. Is there anything in the chat? Because I can't see it. So Norbert or Scott, let me know if I need to stop or move forward.
No questions right now.
Okay. You should try the Gray Scott simulation though, and if you have any questions, send us emails. All right, so next, we are gonna look at the in situ algorithms that are implemented inside ADIOS and that you can use to exchange data between producers and consumers. The number of engines available in ADIOS provide a large amount of flexibility when selecting a configuration. Multiple executables can be connected using the read-write API of any of the ADIOS engines to support a wide range of different types of workflows. And this figure, the workflows that are shown in this figure are being used, so they are used by the data management mechanism for a number of tasks. They're used to couple simulations on multiple resources, either local by doing in situ analysis or visualization, or in transit by transferring data either locally or over wide area networks to remote sites where you can do analysis. Additionally, data from sensors or from experiments can be streamed over the wide area network for analysis and coupled with simulation or analysis codes. Data staging is a generic concept in ADIOS for providing concurrent access to data to one or more consumers through memory or streamed over the network. With staging engines, the data producer will write the data using ADIOS APIs. Afterwards, the data is available to be read by the consumers using, again, ADIOS APIs. And the API is the same regardless of which algorithm you use. The only difference is the engine that you use. So you specify which engine you want to use for your data management, and then underneath, each staging engine has the ability to move the data in different ways. So it's optimized for different things. And these are the main engines that are currently available in ADIOS. SST is designed for in situ infrastructure for staging in a stream-like fashion. So it uses RDMA and sockets. It's the more flexible engine available in ADIOS for staging. Dataman focuses on wide area networks, and it's optimized for wide area networks transfers using sockets and 0MQ underneath. SSC is focused on one-sided MPI, so it uses one-sided MPI and is focused on strong coupling codes. Data spaces is implemented for staging, providing a shared memory abstraction. And inline is the traditional in situ execution of consumer codes that are running on the same resources as the producers. And we're going to look a little bit closer at each of the engines. SSD, it's, as I said, the most versatile and the most flexible staging algorithm used by ADIOS. It uses either remote direct memory access or TCP or UDP or shared memory to move data from a producer to other consumers. And for SSD, we assume that we have a producer, a parallel application is a producer, and consumers can be multiple independent parallel applications. Consumers can come and go dynamically without affecting the producer. SSD has been designed for portability and reliability. The way that it's implemented underneath is by separating the control and data planes. The control plane manages the metadata and the control using message-oriented protocol, inherits concepts from FlexPath and DIMES. The SSD writer engine aggregates metadata for every step and shares it with all readers. Readers then issue remote reading operations based on the I/O patterns in the metadata. This allows the I/O pattern to vary over time. SSD also allows readers to disconnect and reconnect while writers keep writing. So it's a resilient engine. On the data plane side, SSD exchanges data using RDMA. Is responsible, so the data plane is responsible for resource management for data transfer. It uses libfabric underneath for portable RDMA support. And it uses threaded execution to overlap communication with computation and for asynchronous progress monitoring. If we move forward. To address different application requirements, the SSD buffering policy can be configured at runtime. This includes, for example, keeping only the most recent step or buffering a fixed window of consecutive steps or blocking until the step is consumed. In cases where strong coupling is required between applications, the buffer limit can be set to 1. Which will ensure that every step is consumed by the reader before the producer moves on. It's true that it could slow down the producer in this case, but if it's strong coupling that you want this, you have the flexibility to choose depending what your application needs. For use cases like interactive visualization, buffering only the latest step is useful. Since the user typically does not want to block the simulation while a particular time set is explored. So you have this option of deciding the pace that the producer and the consumer go at. SSC, the SSC engine is designed for applications running under the same MPI context. It's designed for application with constant metadata, so it's less flexible than SSD, but if your application would have these restrictions anyway, the performance can be improved. The SSC engine aggregates metadata once on the first time step, so you don't waste time communicating metadata at every step. It uses a combination of one-sided MPI and two-sided MPI methods for flexibility and performance, depending on what the data needs to do. It uses threads and not blocking MPI methods to hide communication time. The one-sided MPI paradigm does not require the send and receive calls to be paired. And this way it allows direct access to remote memory of another process. So in general, the performance for SSC is better than SST. There are a few applications that are currently using SSC successfully. XGC coupled with Gene and Gem is one of this. And this is currently using SSC to couple also with visualization, not only Gene and Gem. And in general, ECP application that requires strong coupling together with in-situ analysis and visualization will probably see better performance using SSC. Dataman focuses on providing good performance for wide area network data transfers, data staging, near real-time data reduction, and remote in-situ processing. It's unlike any other staging engines, Dataman does not guarantee that every data step is transferred. Instead, the subscriber is designed to read only the latest data steps while ignoring the previous steps. This saves the two-way communication for checking step completion. And because of this, the data transfer latency is reduced and can support near real-time analysis better than any other engines. It's designed with a few principles in mind. So flexibility is really important to allow transport layer switching between multiple implementations underneath for data transfer. Versatility to support various workflow models. So P2P query or pub-sub paradigms. Adaptability, allowing adaptive data compression based on near real-time decision-making. And then it can take advantage of all ADIOS transports on operations. So regardless of what operators you have in ADIOS, Dataman will be able to use it. So if you want lossy compression or lossless compression, you can apply it. Target application for this are in general applications that require wide area network. It's been successfully applied in using building dynamic workflows, in streaming data from the K-Star fusion reactor in Korea to compute resources and NERSCs. Also, Dataman is the engine that was used for the Gordon Bell paper that Scott talked about. So it's really successful for wide area network transfers. It's doing this in 3 different modes. So it's capable of using a push mode, where this is a sender-driven model workflow, where the senders are the ones that configure what data they're sending, and then the receivers just subscribe to this. A query mode, which is a receiver-driven workflow, where the receivers are configured to query particular data. And the subscribe mode, which is an ad hoc workflow. It's a free combination of senders and receivers. Senders and receivers can be launched in any order, and they can be attached and deattached freely without affecting any other of the senders and receivers. Data spaces is another engine in ADIOS. This one is an asynchronous I/O transfer method that enables data staging through the use of a virtual shared space. Data space is basically designed for use in HPC environment that want to take advantage of the RDMA network interconnects. It supports a full M-to-N data distribution. So it supports multiple producers and multiple consumers. It has an adaptive cross-layer runtime management, a hybrid in situ and in transit execution. Dataman can extract data from running simulations into the memory of staging servers. So the resources used on the application nodes is reduced, enables more loosely coupled data interactions. And the last engine that is implemented in ADIOS is the Inline Engine. This one provides in-process communication between the writer and reader, avoiding the copy of data buffers. Is focused on an end-to-end case. So we have N writers that shared a process with N readers, and the analysis happens inline without writing the data to a file or copying to another buffer. So the consumer has access to the memory of the producer, and they don't need to exchange data any other way. Target applications are traditional in situ visualization routines that scale well with the producer size. In general, from my experience, for the inline, you would want the consumer to be as embarrassingly parallel as possible. When you choose which engine you want for your application, there are several considerations that you need to look at. And the first two, the system consideration and the coupling consideration, are functionality-based consideration, and then you have performance consideration. So if you want to stage between machines over wide area networks, then you will go with Dataman. If the execution is collocated between the consumer and producer, then you want SSD. If the availability of RDMA is high-speed network, then you can use SSD or data spaces. If you have writers and readers that are highly synchronized, SSC will be better. If you have an ensemble workflow where you have multiple independent writers, or if your data lives independently of any given writer, then data spaces is designed for this scenario. For one writer, many readers, SST will be the best choice. If you have one reader and many small producers, data space or maybe SST will also give you good results. Another one that's not here is if you have resiliency considerations. So if when the reader fails, you don't want the producers to fail, then you might go to SST as well. So depending on your functionality considerations, you will choose one engine over another. And then you have performance consideration. These are harder to understand because they're usually application specific, they're not obvious. But since all you need to change is the engine that you're using in order to run your application with one or the other, it's good that you can use ADIOS as abstraction and figure out what works best for your application needs. So we're going to look at a few examples where we're staging IO, and we're doing it through two different methods. One is through reading from file concurrently, and the other one is by moving the data without using the file system. One output, there are multiple ways in which we can stream data from producers to consumer. We make some assumptions for the example that we're going to show now, and that's that one step is seen at once after the writer completes a whole output step. Streaming in our case is not a byte streaming. It's basically the reader having access to all the data that's generated by the writer in one output step or one ADIOS step. As long as the reader does not release the step, it can read it, which will potentially block the writer. Advancing in the stream means that the writer gets access to another output step, and we lose access to the previous step. So we are moving only forward from one ADIOS step to the other. A few definitions before we go into the examples. A step represents a data set that's written within between one ADIOS begin step and one ADIOS end step. A stream is a file containing a series of steps of the same data set. We open a stream for reading, for step-by-step reading. So we open it and then we go through the stream step by step. And we close once at the very end of the streaming. One step is accessible in streams, and we are advancing it only forward. We use begin step on the reader side to advance to the next step, and we use a variable timeout that tells us how long we can wait for this step to arrive before we return with the step status of failed. If the step status is okay, then we have access to the data, and then inside this if, we can process our data. We release a step if we don't need it anymore. So this is on the reader side. It's basically to allow the staging method to deliver new steps if available. And we do that by ending the step. We go back to the Gray-Scott example with staging. And what we want to get at in the end is to run the Gray-Scott simulation, that's the top box, and then through staging to feed this data to the PDF analysis application and to a visualization code that visualizing the output of the Gray-Scott. And then the PDF analysis is streaming its output to another visualization code that shows you the analysis results of the second application. And first, we're going to look how to do this through file staging, so file-based in situ processing. If we look at the configuration file, so ADIOS is configuration file that the Gray-Scott ensemble uses. We can specify the engine type, and in this case, it's going to be BP4 because we're doing staging through files. And then the timeout parameter, we can specify that through parameters. In this case, it's 10 seconds. So the way to, the classic way is to run the Gray-Scott simulation and then output the data to the file directly. And we do this by using the configuration file that I showed you in the previous slide and just running the Gray-Scott application. In order to start building our pipeline, we can run in two separate terminals, the Gray-Scott application in one terminal and then the PDF analysis in the other. And this is going to be, basically is going to create a pipeline where the PDF analysis code is going to read steps that are written by the Gray-Scott application previously. So it's still going through files. So Gray-Scott is writing through the BP4 engine two files its output, and then the PDF analysis is reading these steps through the file and then writing its own output to storage. All right, a little bit further, we add the third application, which is the one plotting the analysis output. And as before, we're going through files, but this time the pipeline has 3 applications. And finally, we start all 4 applications in 4 different terminals, and we're staging through files every step in the way that the figure shows. Okay, so now if we do the same thing with staging, so we are going to look at streaming in situ processing using the SST engine. In the configuration file, all that we need to change is the engine that's being used. So in all cases, the engine is going to be SST. And now if we start the Gray Scott application together with the PDF analysis, we're going to have staging between Gray Scott and PDF. So the files are not going to be written. The data is going to be streamed directly from Gray Scott to the PDF analysis. And we need to start them together, the 2 applications. The PDF is writing using BP4 its output to storage. If we start the third application that is plotting the output of the PDF analysis, we're going to have staging between every application. So the data is not going to be going through file at all. It's going to be staged directly from one to the other. And we can add the fourth, and then we're going to have staging from Gray Scott to the visualization and to the PDF analysis, and then from the PDF analysis to plotting the results. And then finally, we can change the pipeline and we can play around with how the staging is going to transfer the data from applications to another. And this is the task that you would have had if we were doing hands-on. So instead of having Gray Scott staging to the PDF and to the visualization application, we want Gray Scott to stage the data to the PDF analysis application, and then this one will stage for the 2 plotting and visualization application. And you're going to see that it's not hard to do. There are some hints that are basically telling you how to do this. But what's fun about the SST engine is that you can play around with how you want your data to be streamed from one to another. And this way you can hide the cost of certain applications. So right now, if the Gray Scott application takes a long time, then all the staging that's happening underneath can happen while Gray Scott is executing. So at the end of Gray Scott, you are going to have the visualization of one Gray Scott step. I mean, you're going to have the visualization and the plots of the analysis ready for you to look at. And I think that's my last slide. Any questions here?
Thank you, Anna. You know, you can ask questions again live. We don't have a lot left. Now I have to hit share my screen. My assumption is that I did it once, so I can do it again. Something did not work right, or can you see my screen?
It's not completely. There's okay, now we can see your screen. I think you had maybe some windows on top.
Funny. Okay, slideshow. No, it puts 3 windows up. So you see my screen that says FYI.
Yes,
so,
it does.
Just as for your information, tomorrow, we have a wonderful person hosting data staging and coordination strategies for couple simulation workflows. that's Anna. So she is hosting this and includes various experts in the field who have worked with data staging. It would have included Norbert Podolsky, but due to a certain reason, I will have to step in to be part of that. I would also like you to understand that we're going to have a user BOF Wednesday from 1 to 2:30. And actually, the interesting thing is we have, I think it's 7 or 8 different applications, or speakers representing their science that goes from, all different fields. So they're going to start off by giving 5-minute presentations telling you what's really exciting about their science, and then, how did ADIOS help? And it includes speakers from all over the world. So, I am the partial host with Norbert Podolsky on this. So, again, I'd like to refer you to that. Now, in this whole area of in situ, what I want to say is that what you have to understand is, like, when we talk about this XML file, you do not have to have this. But when you want to be able to switch right at runtime, it's just an input file and allows you to say, you can use this method. And what's the really interesting thing here is that when you want to do some of these complex workflows, you can choose which one goes through files, which one goes through different staging methods. So one of the things that Anna explained is that, you could run your simulation, and instead of using ADIOS to write your data out to storage, it can write your data out that goes to different cores that live, for example, in the same node. So you may have 1,000 nodes, but 1 core per node on, say, Summit, that will do something else. So sometimes when people think of staging, you can think of things as a form of asynchronous I/O. So it stages, that data can just be staged very quickly using in-memory techniques. And, for example, the SSC method, that uses one-sided MPI. So it just simply goes to the other nodes, and then from the other nodes, you could write it directly to storage, or you can perform some calculation. You could run some complex workflow. And as Anna said, there's this whole art essentially to get this perfect. But if you want to just do your science, many of these techniques will work, and if there is a bottleneck, you should just send a message on GitHub, just send an issue. We typically have people who monitor that. Within a short period of time, we'll connect you to a scientist, and we go to great strengths to actually work with you to get this. Now, in the example that would be shown, and I don't know about you, but you see, I have loved to hate Zoom meetings because you don't actually get to interact with anyone. And these tutorials have always been, everyone types, we give someone a virtual machine, we can have Docker containers, but everyone's on their own laptop. You could run small parallel jobs on there, and we would be running these on your virtual machine. So by just showing this, what it's saying is that, again, at runtime, you could do things like fire up visualization, kill visualization. It's, you could change your pipeline. And, this is just showing in a virtual machine where we would fire up, again, visit. And you could do things like when you go and visit, there's a button to essentially play or step. And when you go to the end, you can just click essentially like the step button, it would read in the new time step. So if your simulation, for example, is writing out data, say, every second, but in Viz, you wanted to spend every 60 seconds to look, in this case, it's looking at an isosurface. You could look at some cut planes. This is in, of course, in Python with matplotlib, but you can spend as much time in the analysis and it doesn't slow down the simulation because it is done asynchronous. And that's the beauty of this. So instead of, as I say, doing visualization, you could do reduction and then it could write out. So you can just set up these complex workflows. And that's what we sometimes do with scientists, work in the workflow part of this. And this allows like different things to happen. I'm putting the video again to say, so what Norbert explained in what we'll show here is, this is the gray sky. This is actually running a fairly coarse problem. It's a 48 cubed grid where each process in this run, where it was done on 4 processes, is just getting a 24 by 24 by 48 grid. And as the simulation runs, eventually you can fire up something like staging, and that's over here. And in the method, and this engine will actually be the SST method, you can set it to be blocking or non-blocking. And that's a simple thing in an input parameter, or in what we say is in the XML file, you can change, or in the API. And I accidentally went forward. And when you do that, I should go back a little, sorry. Here, the readout is SST, and it's set to block until something, and in this case, this is the something, the MPI command. Once this connects, it's saying, then this will continue. But of course, the simulation just continues and it doesn't know that anything is connecting. So it has no ability to really understand all the things which are connected to it. It's just publishing and it goes. And if it was done on a machine that had like enough horsepower, not a VM on a laptop, you would see that, okay, this is bad. My system is going back and forth. But when you do this, you'll see then things go. And then when you fire up something else, it just appears. And then, again, visit the way it's meant in its most simplest form. And I'm just pausing a second, but it's meant to think of things in files. So what do you do in a file? You would click on open the file. In this case, it's already set up to have a session, which means there's a session there. And then it basically starts running. The session has, this is doing contour view, isosurface of U, isosurface of V in the plot. But if you wanted, and if this was real, you could stop and then you could change things. In this case, we were changing the angle of the visualization. So you could just stop it. And again, the important thing to point out is if this crashes or you kill it, the simulation doesn't know. And in fact, many of the things that are connected don't know. So you can just kill and you can then run them again. And that's one of the real strengths of this. And when we compare something like this to, say, our SST engine based upon, again, one-sided MPI, in MPI, if something crashes, I think you guys are aware, right now, something crashes MPI, everything will crash. So there's been cases of where we ran with Fusion, and in Fusion when we ran, I'll just pause on the slide to say that we had some of the visualization that for some reason, when we were running at full scale, things just died. But the simulation continued, and we had a fallback that we also had staging right files, so it was fine. The simulation continued. The viz piece was fixed by a very nervous visualization expert who fixed it nonstop, so that then they fired the visualization up. And again, this was on Summit, and it was run in a debug mode so that they could actually fire it up during the simulation. And that allowed us to go much further. So this is the last slide. And I'm going to stop sharing. And I would welcome that both Norbert and Anna, if you could turn your video. So what, typically what we would do, and given that I've seen the ratio of people on starting in the 50s to now in the 19s, I'd like to invite, questions, because again, this is the last thing for ECP, for us at least in the day. And what we want to say is that, we want to be fairly agnostic to file format or even the implementation. So you can use ADIOS, there was a question, and you can just use this API and write out HDF5, and it will be done in a very optimal fashion. So the person who wrote the HDF engine inside of ADIOS was part of the HDF5 developer team. So it's not like you'll have a problem. For certain situations, you'll get more performance writing to a BP engine, but you can go and get all these different options, and whatever works best is the way you want to see this. I see a question in the chat. It could be any one of us to answer. It's, how do you automate the simulation visualization pipeline, manually or have some code script? Let me give you the first answer, okay? And then the others can. Now, in the example that we showed, and Anna showed, Norbert showed, suppose you had your producer, and your producer just has writes, or what we say puts. So in between the begin step, end step, you have a bunch of puts. So let's suppose you push two variables, pressure and temperature. And then that's it. If you use the engine of BP, it goes to the file system, you're done. If you did this manually, and this is again what we're trying to explain, and you have your other code, and you have a Python code for doing your visualization. And what it does is it does an open, it begins steps, it reads maybe a portion of temperature, maybe a 2D slice of temperature, and all the 3D part of pressure. You have that in your analysis code, you have your end step, data is on the file system, you run, and now you have this done. And then how do you automate it? Well, if you're on, suppose you're on a simple platform like Summit or Cori or other systems that we are aware of. In your batch script, you have whatever you want to have. It's MPI, MPI run. You just have 3 MPI runs or 2, how many things you have, you just run them. There's a way to partition depending upon Summit, and you run them all separately, and now the pipeline is from the connects. Norbert, do you want to add to that answer?
Well, yeah. So I think actually the question is not an ADIOS question, right? It's how do we automate these pipelines? And that's not what ADIOS is going to answer you. So everything that Scott said is the ways of automating your pipeline. And in general, the answer was, yeah, pick your workflow system that is able to launch these codes and run them together. So tomorrow at the ADIOS BOF, you will hear an application that used Radical Pipeline to run parallel pipelines applications using the SSD staging and ADIOS on Summit. We use the FIS or homegrown system to drive these fusion code coupling applications. So you need a workflow system. You either go basic manually or your batch scripts, or you have to use a proper workflow system that is able to launch these and control them.
Yeah. Are there any other questions? We're here. We can talk more about at scale. I mean, we have so many apps that we've run with. In fact, one of the participants who was on, he sent me a paper which acknowledged ADIOS He works for a company associated. He just sent me a paper and acknowledged, and it was like, you know, it was very nice because it's like, hey, we're acknowledged in a paper from some people in some company, which was a nice, you know, those are nice things. So we are very inclined to work with applications. So we can stay on for like a couple more minutes if, unless there's no more questions. So again, we're happy to, Anna, you want to put a final plug in for your buff?
Yeah, so tomorrow during the staging buff, we will be talking about other solutions as well. So it's going to be part ADIOS, but also what other labs and other universities are doing for their staging needs. So if you have general questions or just concerns about staging in general, you should join us there and ask tough questions to why staging is needed and how to use it.
Yeah, and I'll just comment for a last second on it. Again, when we say staging, we can mean a very traditional visualization type of in situ. So it's just, you know, shared pointers between the code, and that's that inline engine with ADIOS. Or it can mean you run on, you know, separate cores on the same node. So a few cores every node, you're running those staging things. And or it can mean you, for every certain amount of nodes you run your simulation, you have running all the other parts of your pipeline. And again, there's you know, there's a lot of different choices, even hybrid choices between those. And as Norbert put in the chat window, the placement, that's up to the workflow system. So it's a simple thing, the way I said, then it's just going to be usually separate nodes if you just run with, you know, separate like MPI runs. All right. Norbert, you want to say the last word?
Oh, I'm not good at words. So thank you very much for attending this tutorial. I hope you found interesting piece of information for yourself and learned something useful for I/O.
And if you have any questions, use the GitHub or send us emails.
And I actually, hold it, we have Todd Munson. We heard from him from the plenary, so.
I was not going to say anything, but I just wanted to turn my video on so that you, Scott, knew that I was here for the whole thing. It's very nice, and thank you all.
Actually, Todd, there was a question.
Okay.
Okay. If you're using PETC, can that be hooked up with ADIOS?
Yes, there is at least a version of ADIOS. I believe it's ADIOS 2 bindings for PETC, the same way we did HDF files.
Right.
So I can dig out more information on that. Barry did a quick version. I'm not sure if it's as hardened as one would like, but there is at least a prototype version of it available in PETC.
And what Todd's probably saying is that if you need it hardened, Todd's willing to make sure that gets done.
I will make sure it gets done and make sure everything gets forwarded to the right person so that they can answer your questions, because I'm not the right person to answer all those questions, but I know who can.
Thank you, Todd. All right, thank you very much. Hope you guys have a very excellent day. Bye.
Thank you, bye. Bye.
Bye.